Welcome back to Pump Design Lab. In part 1, we learned that a wall slows nearby fluid and creates a boundary layer that grows downstream. Now we will look inside that layer. The key question is, how exactly does velocity change between the stationary wall and the fast outer flow? What is a velocity profile? A velocity profile is a picture of how fluid speed changes from the wall outward. Imagine a graph. One axis represents distance away from the wall, and the other represents fluid velocity. At the wall, velocity begins at 0. As we move outward, the velocity increases until it reaches the free stream value. Every velocity profile begins at one non-negotiable condition: the fluid velocity at the wall. Velocity at the wall. The most important point on every boundary layer profile is the wall itself. At a stationary wall, the velocity is 0. This is the direct expression of the no-slip condition. It does not matter whether the outer flow is slow or extremely fast. The first layer at the wall is held back by the surface. From that stationary wall condition, the velocity gradually recovers as we move outward. Velocity away from the wall. As we move away from the wall, fluid is less directly affected by wall friction. Its velocity rises gradually. Eventually, it becomes almost equal to the main flow velocity. The boundary layer is the entire region over which this gradual recovery from 0 to full speed takes place. This gradual recovery is worth emphasizing because it is easy to imagine it incorrectly. A ramp, not a cliff. It is important not to imagine a sudden jump from stationary fluid to fast-moving fluid. Real fluid gives us a smooth ramp, not a vertical cliff. Viscosity continuously transfers momentum between neighboring layers. That is why the velocity curve changes smoothly from a wall out to the free stream. The shape of this ramp is not only visual. Its slope has a direct physical meaning: shear stress. Velocity gradient. The steepness of this velocity ramp is called the velocity gradient. Near the wall, the gradient can be very large because velocity rises from 0 over a small distance. This gradient matters because wall shear stress is related to it. A larger velocity gradient generally means a larger friction force between the wall and the fluid. Let's now translate that velocity gradient into the actual friction force acting on a wall. What is wall shear stress? Wall shear stress is the friction force per unit area acting between the fluid and the wall. The wall pulls backward on the fluid, opposing its motion. The fluid applies an equal and opposite friction force to the wall. In a pump, this shear stress exists over all wetted surfaces, and the total effect contributes to hydraulic loss. But friction alone is not the entire story. The shape of the velocity profile also tells us how strong or weak the near wall flow is. Why profile shape matters. The profile shape tells us whether the fluid close to the wall still has enough forward momentum. A full, healthy profile has relatively strong forward motion near the wall. A weak profile has a large zone of very slow fluid close to the surface. That weak near-wall fluid is the first part of flow to fail when it meets a rising pressure. We can describe that weakness more precisely as a momentum deficit. Boundary layer as a momentum deficit. Compared with ideal flow, the boundary layer carries less momentum because friction has slowed it down. You can think of this as a momentum deficit near the wall. The outer flow may still be moving strongly, but the low-energy region close to the wall has less ability to resist a difficult pressure rise. This is a hidden weakness inside every boundary layer. This is exactly where the idea becomes important for centrifugal pumps. The first pump connection. Inside an impeller passage, velocity profiles develop on the blade surfaces and on the hub and shroud walls. These layers occupy part of the flow passage and reduce the region carrying high-energy flow. They also make the exit flow non-uniform. This affects the real outlet velocity triangle, the hydraulic losses, and ultimately the head and efficiency of the pump. Velocity profile is a ramp, not a cliff. Before continuing, let's summarize what the profile has taught us. The boundary layer is a smooth velocity ramp from 0 at the wall to the outer flow velocity. Its steepness creates wall shear stress. Its slow region represents a momentum deficit, and its shape tells us whether the near wall flow is healthy or approaching separation. So far, we have described a boundary layer as though it always behaves smoothly. In reality, it has two very different possible personalities, laminar and turbulent. Two personalities of a boundary layer. Boundary layers do not always behave in the same way. They can be laminar or turbulent. A laminar boundary layer is smooth and orderly. A turbulent boundary layer contains chaotic mixing and small eddies. These two states have very different friction losses and very different abilities to stay attached to the surface. Let's begin with the more orderly state, the laminar boundary layer. Laminar boundary layer. In a laminar boundary layer, fluid moves in smooth layers that slide past each other in an organized way. There is little mixing between layers. A particle close to the wall tends to remain close to the wall, while a particle farther out tends to remain farther out. The motion is quiet, predictable, and orderly. Because this motion is orderly, it has one important benefit: relatively low friction. Why laminar flow has low friction? Because laminar flow has little mixing, often produces lower skin friction drag than turbulent flow. Imagine traffic where every car remains in its lane, moves smoothly, and makes no sudden changes. The result is orderly motion with relatively little disturbance. Laminar flow can therefore be desirable when surface friction reduction is the main objective, but low friction does not mean that laminar flow is always the best possible condition. The limitation of laminar flow. But laminar flow has a weakness. The slow fluid close to the wall is not constantly replenished with high momentum fluid from outside the boundary layer. When pressure starts rising downstream, this near-wall fluid can lose its forward motion quickly. So laminar flow often separates earlier than turbulent flow in an adverse pressure gradient. As flow continues and disturbances grow, a laminar boundary layer can change into something much more mixed. Transition from laminar to turbulent. As the boundary layer grows, the smooth laminar pattern may become unstable. Small disturbances from roughness, vibration, upstream turbulence, or high velocity can grow instead of dying out. The flow then changes through a transition region and becomes turbulent. Reynolds number helps us judge whether inertia is strong enough compared with viscosity to encourage this change. That new state is the turbulent boundary layer. Turbulent boundary layer. A turbulent boundary layer contains many small, irregular swirling motions called eddies. Fluid mixes strongly across the layer. Fast fluid from the outer region is carried toward the wall, and slow fluid from near the wall is carried outward. The motion is more chaotic, but it also changes the momentum distribution in an important way. This strong mixing improves one aspect of the flow, but it also comes with a cost. Why turbulent flow has more friction? This strong mixing transfers more momentum toward the wall. As a result, turbulent boundary layers usually have higher wall shear stress and higher skin friction loss than laminar layers. Turbulence is therefore costly if friction drag is the only concern. But in many real machines, separation is a much larger loss than the added friction. The surprising benefit of turbulence is that it gives the near-wall fluid more energy and momentum. Turbulence has a superpower. The major advantage of turbulence is that it brings high-momentum fluid down close to the wall. This re-energizes the near-wall region. The turbulent velocity profile is called fuller because more of the layer moves at a velocity closer to the free stream value. That fuller profile can keep moving forward even when pressure rises downstream. This creates one of the most important trade-offs in fluid mechanics. The engineering trade-off. This creates a classic engineering trade-off. Laminar flow gives lower friction but may separate easily. Turbulent flow gives higher friction, but resists separation more strongly. The correct design choice depends on the situation. If early separation would create a large wake, a stall, or a major diffuser loss, a turbulent boundary layer may actually provide the better overall performance. In the next episode, that trade-off becomes critical. We will see why a low-momentum boundary layer can detach from a surface, creating separation, the source of some of the largest losses in pumps and diffusers. Laminar and turbulent boundary layers. From this, we can able to understand that laminar boundary layers are smooth, orderly, and relatively low drag. turbulent boundary layers are mixed higher drag and fuller near the wall. The important lesson is that turbulence is not automatically bad. Its mixing can give the boundary layer the momentum it needs to remain attached. That is the end of Part 2, Velocity Profiles, Laminar Flow, and Turbulence. Next, we will explain boundary layer separation using simple analogies, aircraft wings, diffusers, and a surprising lesson of a golf ball. Subscribe to Pump Design Lab for practical, step-by-step explanations of pump hydraulics and rotating fluid machinery.